on YouTube. And we should be ready to go here in just a second. Let's see if this is live on the internet. Let's see here. Where are we? I think we are live. Yes. Let's see here.
Okay.
Live. And I'm going to go to make sure people can see us out on the internet. It is a great pleasure to have you today, Roger, Sir Roger Penrose. Let me just make sure we are broadcasting to all the places we want to be broadcasting to. Yes, I believe that we are. I see it. We've got already 34 people are watching. There we go. Great. Okay, everybody, welcome to this episode, a very special episode of the Arthur C. Clarke Center for Human Imagination's Into the Impossible podcast, featuring my friend and a collaborator, Sir Roger Penrose. Roger, welcome to you.
It's a great pleasure. Thank you.
And has anything happened to you since the last time we spoke? Any news in your life since the summer?
It was a little thing I heard a few weeks ago, yes.
Yes, so first I want to wish you a hearty congratulations for your receiving of the 2020 Nobel Prize in Physics, a half of a share of the Nobel Prize, and I do want to talk about that as we go live. I do put out slides for this that people can find in the YouTube chat box. So if people are interested in following along, I will show some slides along the way. So I'll give you guys a couple of seconds to get to those slides. They're in the chat and in the comments, and these are regarding the subject of today is not going to be Sir Roger's Nobel Prize. At first, we're going to talk a little bit about that because I think people are curious about it. But we're also going to talk about a wonderful book that's made a huge impact on me and many other people, and that's his book Cycles of Time, which came out in 2011, one of the formative books of the early part of the last decade that describes in some detail Roger's very curious and provocative conformal cyclic cosmology. And to understand it, I think it's helpful to have some preliminaries about the way that the the model was developed and devised, and what made you come up with it, essentially. But first, I want to ask, where were you when you got the phone call that you were a recipient of this particular gilded medal here? How did you find out?
Well, it was a bit curious because it was a bit protracted, you see. I think the first sort of faint notice was when I was just coming out of the shower, so... But it was a call from my PA, Petrona Winton, and she told me she'd had this strange message, and somebody wanted to know my phone number, and she said she didn't give my phone number out, you see. And then she sort of started to get a little bit suspicious, and she said, "Is it about a prize?" And they said, "No, we're not allowed to say anything." So she phoned me up. You see, that's when I was just coming out of the shower, and I thought, well, I have no idea what this is about, but I don't see any reason why you should give my phone number. So she did give my phone number to them. I just waited a long time, and then nothing happened. And then finally I did get a phone call from somebody from the Academy of Sciences in Sweden, so it was getting a little bit more suspicious. And she didn't say what it was about. But she said that in a little while the director would phone of the Academy, or whatever he is, was going to phone me up. So nothing happened again, and so I think I went with something else. And then the phone did ring, and he did introduce himself and started talking to me. And then he said, "Oh, would you hang on for a bit?" So I waited and I waited and I waited and I waited, and then I just hung up. If it's something important, he'll call me back. So he did call me back eventually, and he said it was a Nobel Prize. Yes.
Wow. And so did you react honestly to feel like it was an overdue occasion for this, or did you think that by endorsing my book, Losing the Nobel Prize, that you were finally out of it? I'll remind you what you said. You called it a fascinating autobiographical account full of intriguing detail of the passions and inspirations that underlie the scientific quest. A highly thoughtful and informative book. I think this for me was the last. You're the closest I'll ever get to having a real, not chocolate version of these. But did you feel like it was long overdue? I mean, a lot of people speculated that your good friend Stephen Hawking, who we'll speak a lot about today, obviously, that he deserved a Nobel Prize and that he was unfairly overlooked, so to speak. What were your reactions? It took a long time. The prize says that you must give it to someone in the preceding year, and you've been making contributions every year, but the award citation really cites work done perhaps many decades ago. So did you feel like it was expected or totally unexpected? How did it react to it on a personal level?
The trouble is, various people had told me that it was overdue, so I had to believe. No, wouldn't have expected it at all. Apart from what people, some people seem to think that. I mean, the work I did, as you say, was ages ago. It was actually 1964 when I did the work. The paper was published in 65. And that was at a time when the quasars they'd been around for a bit and people were puzzling about them because they seemed to be so bright and yet so small from the timing of variations, that they had to be of a size comparable with what's called the Schwarzschild radius. And people knew that if anything was that kind of size, they would collapse. I mean, there was a paper in 1939 by Oppenheimer and Snyder, where they had described the collapse of a dust cloud. And this was basically the picture of collapse to a black hole. But people didn't take it very seriously, most particularly Einstein, who was in the same institute. I'm not even sure Einstein even read the paper. But I think what people thought was two things about it. One was it a collapsing dust cloud, and dust has no pressure, so you might think it's nothing to stop it. The other thing, more important, is that it's spherically symmetrical, so everything simply falls in towards the center with nothing to stop it. And so it's not so surprising that you would get an infinite density in the middle, and this would be a catastrophe. You don't know what to do with it. But people thought, well, that's very unrealistic. In any realistic situation, apart from the pressure, which actually works the other way, and pressure doesn't help you. But apart from the pressure issue, you wouldn't expect this thing to be exactly spherically symmetrical. So you'd think it would collapse inwards, get very dense, and swirl around and come swishing out again. This was also sort of confirmed, in quotes, by a paper by Lifshitz and Khalatnikov, two Russians, who appeared to have proved that in the general case, you would not get singularities. So this place of infinite density or some catastrophe like that would not happen. And so it would swish around and presumably come out again. I looked at the paper and I didn't notice the mistake in it. There was a mistake in the paper, but I did feel that arguments of that sort were probably not too persuasive to me. And so I didn't think it was conclusive. And I started thinking about visualizing myself being inside a collapsing collection of matter. And I more or less came to the conclusion that you couldn't prove anything just by local argument. It had to be something global, something more, not in one place, but in a sort of some surrounding region. And this was a key thought, that it was something non-local. And later on, I came to this. There's a story which I've told people often about when I was talking to Ivor Robinson, who was an Englishman who worked in relativity theory in Dallas, Texas, mostly, and he was visiting back home in his home country and talking to me. And he was somebody who had the real gift of the gab. I mean, artistically, he was a wonderful speaker. And he was just talking to me, I don't know what, about. And then we got to this side street where we had to cross the road. And the conversation stopped when we crossed the road. And then we got to the other side, it started up again. He told all sorts of exciting things he was telling me about. And then he went home, or went off somewhere. And I came away thinking, having this strange feeling of elation. And I couldn't think why I felt like that. So I went through all the things that happened to me during the day, what I had for breakfast and what I did after that, and did I have a walk or catch the tube, or I obviously caught the tube. But what it was. And then eventually, working through all the things that happened, I got to this time when we crossed the street. Now I realized in that time crossing the street, I had an idea, which was, I think, the idea of what I call a trapped surface. I later called a trapped surface, which is a surface. I can actually describe what it is. You think of a surface, an ordinary two-dimensional surface, and it's closed up. So it's like a spherical surface. It doesn't have to be a sphere, but imagine it's closed up. And that surface, you imagine a flash of light occurs on that surface. Now, normally, if you have a flash of light on a surface, if the surface is bendy, it'll be concave on one side and convex on the other. And the concave side, the light will be converging. On the other side, it'll be diverging. But in this curious case, when you get in this beyond this point of no return, it's what we now would call inside the horizon. But when you're at that stage, you can find surfaces where the flash of light, both the inward flash and the outward flash, are converging. So the light rays are coming together on both sides. And I knew that this would be bad news from studies that I'd done previously of looking at future sets. You look at you'll have sets in space-time, and you see what region can you reach by time-like curves, that is particles which don't travel faster than light. What kind of region do they sweep out? And what's the boundary of that region, and what does it look like, and what is it generated by light rays, and what do the light rays do, and how do they reach their caustic surfaces and crossing regions and so on. And I was familiar with that, and I realized that when you had this situation, you're going to have trouble. And there's no real way. I mean, there are various sort of loopholes, but no serious loopholes. As long as the energy density doesn't go negative or something like that, you would definitely have to have a singularity. And so this was the paper. I wrote this paper and said that singularities were necessary in collapse. The main point about this is that you don't make any assumption of symmetry. You can take the symmetric case and then wiggle it around, as long as you don't wiggle it hugely. So it's qualitatively fairly similar, but doesn't mean that the matter has to fall towards the center. It can be quite complicated any way you like, as long as it starts in this sort of converging state, and then it necessarily you get a singularity. I had a slightly awkward point in the proof, which Charlie Misner improved later on. So it was.
I want to ask you about that in terms of collaboration, etc. But first, before we get to that, so I'm showing a slide from a picture from Cycles of Time, where you describe this infall into the singularity. This summer, you were quite busy this summer, maybe in anticipation. Your third eye or something knew that you were going to be very busy, and I do want to take the time to appreciate you and to recognize and express gratitude for being on the show in such a hectic time. You have to prepare your Nobel lecture, etc. But I was inviting you over the summer, and the timing didn't work out for you to be on our podcast discussing theories of everything with our guests. We ended up having quite a lovely series of guests this summer, and and we were entranced by these ideas about theories of everything and how they could perhaps unify quantum mechanics with gravity. And a lot of what I took away from that discussion was kind of a new doubt that singularities exist, and not to offend you in any way, but we have no physical evidence of a black hole singularity, and the converse process we'll talk about. You talk about falling into the black hole and what you would see once you pass the event horizon with all the light cones tilting towards the singularity, and all paths, all world lines will terminate on the singularity. But are singularities also a matter of faith that a physicist must have, or do we have any evidence of anything in nature that is physically infinite in any regard that we have evidence for?
I think the answer to that question is we have things in aerodynamics where you get shock waves and so on. I mean, but then you say the physics that you've been using at some point you have to replace by a more refined physics. Mm-hmm. And so the idea here, and this is what I certainly stated in the paper, was that maybe you have to consider quantum gravity. That quantum mechanics, classical theory of general relativity, which is a classical theory of gravity, doesn't combined with quantum mechanics. And so when the densities get enormous, you might expect that quantum effects would start to become important. Densities getting, or the curvatures become enormous. And so the classical description would become inappropriate. No, I was quite prepared to accept that. But in a sense, well, you see, I tended not to use the word singularity in most of the discussions. I'm not quite sure I remember what I said in that particular paper. It was in the title, but I don't know whether I'd certainly considered other possibilities like this.
Well, ask people in the chat room. Can you look up the title of somebody post that in the chat for Sir Roger? Because I've forgotten it too. Yes.
I think it's in the title.
Yeah. So somebody out there, please. We have got hundreds of people listening right now. So somebody will post it in the chat room for us.
Yes. Gravitational collapse and space-time singularities. Actually, I can't remember because I've written so many papers.
Just 400 by my count, Roger. It's
but not on that subject. Other subjects. Yes, but you see, it was more Stephen Hawking when he started working on the cosmological singularity that he tended to use the word singularity. And I think he more or less converted me to using it later. It's just a useful term. It's a singularity in the classical theory, but it doesn't mean that physics gives up. It might be that the physics does something probably more where quantum mechanics is playing a more important role. So I was quite prepared to believe that. In fact, that was the sort of view I had. But that led to other things. You see, I've been trying to work on this Nobel lecture, you see, and there are two sides to it. One is what led up to it, that paper, basically. Mm-hmm. And what grew out of the paper is a second part. And what grew out of it, and I mean, I can sort of go through it if you like.
Mm-hmm. Yeah, of course.
First of all, well, Stephen Hawking picked up on the techniques I was using. I should say that I gave, the first time I talked about this was a lecture I gave in King's College London. And in the movie, you see Stephen Hawking sitting in the audience with sparks coming out of his head of inspiration or whatever it is. The trouble with this was he wasn't actually there.
Right. I mean, Hollywood got something wrong factually in science.
Well, it's not quite so bad because Dennis Sharma, who was a good colleague and friend of mine who was in Cambridge at the time, and he educated me a lot on physics. He was a crucial person in my education in physical sciences, particularly gravity and other things too. And he asked me if I'd give a repeat talk in Cambridge, and I said sure. And in January, early January, I gave a talk. I think it was early January, and Stephen Hawking was at that talk. It was a repeat of the one in London.
Is that when you met him for the first time, Roger?
It's when I met him.
Wow.
Yes. It wasn't just he was present in the audience. I had a special session with him and George Ellis.
I see. Mm-hmm.
Possibly Brandon Carter, I can't remember, but George Ellis was certainly there.
Sure.
And we talked about the details of the argument I'd used. They were looking at something not nearly so general as what I was doing. And then Stephen picked up very quickly on these arguments and used a version of my theorem in the opposite direction in time to prove a result in cosmology. But it was not a terribly strong result, and he developed the techniques considerably beyond what I had done and eliminated many of the loopholes and applied it to cosmology as well as to black holes. And then later on we got together and wrote a paper which more or less encompassed the results which we'd done before. But you see, Stephen picked up on the sort of the Big Bang end of it. And an important thing you see about general relativity in most physics is that it's symmetrical in time. The theory works one way just as well as it works the other way. So if you expect to get singularities when matter is collapsing in the future, you would expect to get singularities the other way around when matter is diverging away from a very dense state in the past. Mm-hmm. And so this is the picture of the Big Bang. And the question is this a generic thing too? I mean, can you perturb it in some way and maybe get rid of the singularity? So you might imagine instead of having a Big Bang, which is the beginning, you might have had a previously collapsing phase, which somehow swirled around in a complicated way and then came swishing out again. Mm-hmm. Now, the next stage in the story was when I was, I think I was in Princeton again. I should say I was in Princeton when the quasar things were getting there, and so I was worrying about well, I wasn't actually in Princeton when I thought of the theorem, but it was just a little after that. But I was in Princeton again, and they used to have these meetings in Stevens Institute in Hoboken, New Jersey, which was a short drive from Princeton. And many people used to go there, and they would go there from other universities in New York State. And it was a good place of getting together, thinking about things in relativity. That was mainly to do with that. And one of the cars, I noticed that one of the cars that could have taken me up there was full. But in the car was Jim Peebles, who was the previous physics Nobel Prize winner. Last year.
Yeah.
But I saw when he was there, I took my opportunity. I said, you cosmologists, there are many, many cases where you can get singularities and models, and they could expand from singularities and all sorts of different kinds of models. Why don't you consider these in cosmology? And he looked at me and he said, because the universe is not like that. And I thought, gosh. I assume he meant by evidence from the cosmic microwave background. And you see this very uniform radiation coming with all very, very tiny variations in temperature. And this is a pretty good indication of how very, very uniform the Big Bang was. So I thought, my gosh, it's very, very different. And this sort of bugged me for a long time. You have the singularities in collapse, which are very complicated and hugely diverging. I should say something now about the kind of physics or the kind of curvature you get in space-time. In four-dimensional space, you can have two kinds of curvature. One of them is called the Ricci curvature, R-I-C-C-I, and the other is called the Weyl curvature, W-E-Y-L. Now, in kind of work I'd done earlier in looking at spinors and general relativity, which is an important motivational thing in my case, you can see very easily that the thing splits into these two parts. Now, the Ricci curvature is directly what's given by the matter. So you have a matter density, and that gives you, just there where the matter is, Ricci curvature. Now, when you don't have any Ricci curvature, there's the other kind, which is the Weyl curvature. Now, Weyl curvature describes the gravitational field. This is the way, it wasn't necessarily the way most people looked at it. They tend to think of the metric as giving the gravitational field. But the curvature describes free gravity or gravitational waves or the gravitational field. In the same way that as in electromagnetism, you have the electromagnetic field and you have the sources, which are the charges. So the charges are the analog of the Ricci tensor, and the electromagnetic field, that's the analog of the Weyl tensor. And it's important to get this distinction. Now, in the early universe, you get very, very big concentration of matter. That's Ricci curvature. But what about the Weyl curvature? Now, you see, I began to realize, and this is a big factor in the whole discussion, is this difference between the type of singularity you get in the past, that's the Big Bang, or in the future when black holes, is, the curvature is very different. But the other point of importance is this very, very important principle in physics, or what's called the Second Law of Thermodynamics. Now, the Second Law of Thermodynamics tells you that entropy, now entropy is a sort of measure of randomness. Think of it as just a measure of randomness. The entropy increases with time. That's the second law of thermodynamics. It might have little fluctuations where sometimes it goes down, but the general trend is it increases with time. Now, an important factor in this is the work done by Bekenstein and Hawking, where they showed that there is an entropy assigned to a black hole. And this entropy is proportional to the surface area of the horizon of the hole. I think it's important, first of all, I don't think I just made this point earlier, that people got very confused in the early days about the horizon and the singularity. Because the way that Schwarzschild originally wrote it down, the solution of Einstein's equations, which described the spherical asymmetrical body, the way he wrote it down is you have this place where the things seem to go haywire. Mm. And this was called the Schwarzschild Singularity. Now, this singularity, if you think of the sun, for example, and you imagine squashing it down, you see, the Schwarzschild solution applies to the vacuum outside the sun, but within the sun, you've got matter. And so that particular solution doesn't apply. You have another one. Schwarzschild had another solution, which people don't take very seriously. But the main point is that you have a different solution when there is matter. So outside you get zero, and that's what we normally call the Schwarzschild solution, is the outside of the sun's body, or say the sun. Now suppose you imagine that the sun contracted to smaller and smaller without any radiation or anything coming out. If it were to contract, then you have a bigger region of vacuum and a more concentrated region of matter. Now, if you could squash it right down to, I forget, a couple of kilometers or something, I forget what the diameter is exactly, you get to this Schwarzschild so-called singularity. And people thought, oh, well, that's just nonsense, and you can't deal with it. But various people realized, one of the most important of these was Lemaitre, who was a very important cosmologist. He was a priest, a Belgian priest, and he discovered solutions of the answer. Well, there was Friedman originally, but Lemaitre looked at the Big Bang, and he was a big promoter of the Big Bang. And he was the person who really, I guess, persuaded Einstein you had to take these things seriously. But he also realized that if you sort of let matter fall in, it could cross through this region, which used to be called the Schwarzschild Singularity, and it's not a singularity. It's what we now call a horizon. So this is a region where matter can fall in, and once it's got through this region, it can't get out again. It's a sort of one-way trapdoor or something. It gets through the surface, and there's no escape. And in the spherically symmetrical model that Friedman Friedman was talking about cosmologies, so that Lemaitre had, you see, you have this picture of a black hole, and then Oppenheimer and Snyder later on had this collapsing dust cloud, which was the same sort of picture. And you could see in both those models that the horizon, what's r equals 2n, this is in the sort of units that's used in relativity theory, r is the radius, m is the mass, and when the radius reaches twice the mass in these curious units, then you get to this radius. But it's not a singularity, it's a horizon. Horizon meaning you can fall through it, but you can't get back out again, or light can't get out again. That's the key point. Light can fall in. Light thinks it's going out, but it's actually falling in, if you like, as it goes through the horizon. And the pictures that I like to draw, we have these cones.
Yes, I'm showing that on the screen. I have the slides, and remind people they can download the slides on the link I'm putting in the comments and chat. You can get these very slides, and I'm showing not only the black hole conformal space-time diagram, but also the white hole, which, as you say, violently, I mean, this is as violent as Sir Roger gets. It says violently disobeys the second law of thermodynamics, and so I want to understand that. So yes, keep going. I'm showing the picture as you're speaking, Sir Roger.
Yes, we see the black hole by this Bekenstein-Hawking formula. Bekenstein had a sort of general physical argument to show that the surface area of this horizon would be a measure of entropy, but he didn't know exactly the formula. And then Stephen Hawking had a much more refined argument to show exactly that the entropy was given by this area, a quarter of the area in appropriate units. And this turns out to be an absolutely stupendous value. So if you consider now, with the sort of sizes of black holes we know are out there, the amount of entropy in the current now in the current universe is almost entirely in black holes by an absolutely enormous factor. Now, I was aware of this enormous factor, and Don Page, who I used to talk to quite a bit, he looked after Stephen Hawking quite a bit when he was, I think Don was a graduate student at that time. But Don was very good with the figures. You could ask him something like this and we'd come up with a precise figure. And he just told me how enormous this entropy was in these black holes. And this made it clear that when you get clumping of material, and the material clumps more and more, and finally it produces black holes, this is you can see this is the second law in action. Now, it's curious the way gravity behaves. It's rather, you see, it's misleading in many ways. People think of a gas in a box or something like that. And you might have a gas which is in one corner of the box with some kind of compartment, and you release the gas and it spreads out through the box. Now, that's an increase in the entropy. So you have an irregular distribution of gas, which is a low entropy state, and then it spreads out through the box, and this is getting to a higher entropy state. So as the gas spreads out through the box, the entropy is increasing. Now that's the sort of picture you get with a lot of materials and so on. But gravity is the opposite. You have things spread out, and that is low entropy. And then when the material clumps together, that represents increasing entropy. So the picture is sort of the opposite. But nevertheless, it's still the second law to get uniformity to clumping. And we live off it. I mean, forget about the black holes. The sun's out there, and that used to be just a distribution of gas spread out uniformly. And as it clumped together, you got this hot spot in the dark sky, and that gives us the entropy which we live off life. Schrödinger wrote a book called What is Life? And he was the first person really to point this out. This distribution, this disparity between the hot spot of the sky, which is the sun, and the cold, dark sky is what we live off.
Yeah.
So you get photons from the sun, which are high frequency, and there are relatively small number of those photons, and then the infrared photons, which escape back out into space, carrying essentially the same energy that comes in. So we don't get energy from the sun. This is a misleading thing people think. We don't get energy from the sun because the energy just goes back out again at night. But it goes back out in a high entropy form because there are many, many more photons taking the energy out than came in from the sun, because the frequency going out is lower. And by Planck's famous formula, you need more of them to carry the same energy, and therefore more degrees of freedom, and therefore there's more entropy. So that carries the entropy away, and we get the sun as a source of low entropy. That's the key point that Schrödinger made.
And I want to point out, Sir Roger, just to stop you for a second. So there is you can buy a copy of What is Life, Erwin Schrödinger's book, and the foreword is written by none other than Sir Roger Penrose. So you guys are linked together, both electronically and intellectually, and by this prize here that I resist eating all the time. But go on, Sir Roger. Yeah, so we live on this differential in entropy and energy, not the energy and heat from the sun, but instead from this large differential and processing of entropy, correct?
Exactly, that's right. And that was Schrödinger. I've always been a great admirer of Schrödinger. He's one of my I'm a great fan of him.
Yeah.
In fact, I learned general relativity from him, of all things.
Really? How did that come about?
No, he has this little book called Space-Time Structure.
Oh, I'm not familiar with it. Okay, I'll have to look at it.
You can ignore the last chapter where he goes on to some unified field theory, but everything else, and he does describe these things in a nice, friendly way. I always liked.
Would you say that influenced you? Sorry to interrupt, Roger, but would that influence you in your pursuit of the soft and wet world, in other words, consciousness, that later drove you into learning about consciousness? Would that be attributable to Schrödinger?
That's a complicated story. I would say not so directly, no. Mm-hmm. But I mean, in a certain way, I certainly had been influenced by Schrödinger, and that book in particular, yeah. But,
so getting back to the white holes and the black holes analogy, how does it violently disobey the second law of thermodynamics to have a white hole? After all, wouldn't that be analogous to the Big Bang singularity that Hawking and you and others have worked on?
Well, you see, it has a big entropy. It still has the same Hawking entropy, but this entropy is high. So you see, if it were to evaporate away, imagine the collapse to a black hole, or the white hole would expand out to become a distribution of material, and that would be a huge reduction in entropy. So it goes violently, as I said, I suppose, against the second law. Because if you just simply reverse the collapse to a black hole, you have a relatively small entropy to begin with in the material, which goes enormously up as soon as it crosses the horizon, and the entropy goes absolutely shooting up. So you have the opposite behavior, which is just dreadfully against the second law. Now, you may say second law, people often say, oh, it's just a statistical thing, and so it's not so fundamental.
Mm-hmm.
But I don't know. I think it is very fundamental. And it's fundamental because what started it off. And what started it off was the fact that there were no white holes in the beginning. We had no Weyl curvature. You see, I put this hypothesis, this is just a hypothesis, like everybody else at the time, I thought you had to describe singularities by quantum gravity. And so, yeah, I was certainly of that view, that why you sort of resolve the singularities in black holes, or how you resolve it, would be through some kind of quantum gravity. Nobody knows what the correct theory is, but that would be how you do it. Now, how would that theory apply to the Big Bang? Well, maybe it resolves that singularity and maybe gives you a bounce instead of a explosion. But the nature of the singularity, since my sort of brief conversation with Jim Peebles in the back of the car, I had to get in another car, it was full. But that persuaded me that the universe started out as a very strange, low entropy initial singularity. And it's low entropy in gravity, not in the matter. The matter seemed to be pretty well thermalized, as much as you could have, as far as one could see. That's not where the low entropy resided. Low entropy resides in the fact that the gravitational degrees of freedom were not activated. And this is what I sort of postulated as what I call the Weyl curvature hypothesis. That is that past type singularities, like the Big Bang, for some reason, had to be zero Weyl curvature. The singularities in the future, the black hole singularities, would be wildly diverging infinite Weyl curvature. And the matter might have even been wiped out by then. So perhaps it's almost entirely in Weyl curvature at that point. And this is a huge discrepancy between the two types of singularity. And at that time I thought, well, this tells us that quantum gravity, whatever, just must be a really, really odd theory. So, all right, I thought it was an odd theory, but maybe this all tied in with sort of beliefs I had that somehow gravity was responsible for the collapse of the wave function. You see, and that was a view which I still hold, but not in quite the same way, because I don't think that the quantum gravity is really what's responsible for the Big Bang singularity.
So that's provocative as well, and that actually connects to this conversation that we had over the summer with Eric Weinstein, Sabine Hassenfelder. We had Lee Smolin, your friend Lee Smolin, and for a bit we had Lisa Randall before she cut out. But we had this discussion as to whether or not there really is a need for quantum gravity, and to keep beating on a dead horse, or even is there a need for a theory of everything? In other words, is it, if God, I know you and I have talked about God on previous podcasts, but just stipulate for the time being that,
which you get by playing around with the Schrodinger equation and doing something different from it, from evolving the Schrodinger equation, evolving according to the Schrodinger equation. So you suddenly throw the Schrodinger equation out the window, pull in something else, gives you probabilities, wheel that out the door again and bring back in through the window the Schrodinger equation and go ahead, back again. I mean, it's completely inconsistent what you do. Now, all sorts of people worry about this. Lots of physicists don't. They say, well, we just take the theory as it is. When we make a measurement, we do what we're told, and so on. And that's fine. It works well. People who do quantum mechanics in some practical way always do that. People who are more philosophically minded worry more about what's really happening. They might say, well, things get so complicated, you can't very well use the Schrodinger equation, and you do something else. If you look carefully at what you do when you do something else, you see it cheats at some point. It always cheats. It has to cheat, because the Schrodinger equation doesn't say you get alternative probabilities. It says you get this complicated state which involves superpositions of different alternatives. So that's the
The measurement problem, the quantum interpretations, foundations. So, but is it true that, I heard it once said, maybe it was another one of your co-laureates who said something like, quantum mechanics needs interpretations like birds need ornithologists. In other words, we love to have, kind of a neat way of describing it. But I know for sure that Richard Feynman, a definite co-laureate of yours, said something to the effect that the word is not the thing, and being able to, for us to understand it, it just means that there's a lacuna in our way of describing it. And even if we can describe it satisfactorily, that doesn't mean we truly understand it. The fact that we can write down classical, general relativity doesn't necessarily mean that we truly understand it, because it would have things in it necessarily so. But I think one crisp question for you is, what if there was no singularity? Would that, but it was a very dense object, extremely dense, denser than anything that we can imagine, but not truly infinitesimal in extent. Would that affect the observables in any of your theories of black holes, or, as we'll come to later, in Triple C?
Well, it doesn't make much difference, you see, because we're not going to see the singularities, and you can travel into. It wouldn't be. You take one of these really big supermassive black holes, you could probably take your spaceship, go into it. I don't know how long, probably a year, maybe. I don't know what the details are. You could play cards, or you could try and work out what the space-time is doing out there, and you observe things outside. You could still look at the universe outside. You could have a decent time of life for a while, and then curvatures start to get so big that you get ripped to pieces. But still, you wouldn't know what happened to the singularity, because you just run into it. You wouldn't see any other singularities. Certainly, if cosmic censorship is correct in the sense I like to see, you wouldn't even see any of the other singularities. It's wrong to think of it as a point, really. That's one of the things when you look at the proper structure of things. The singularity is really a space-like region which you run into. But that doesn't matter too much.
It's funny because we'll have on a friend of yours, hopefully in a little bit. Jan 11 has agreed to come on just to wish you a hearty congratulations later. I'm hoping to patch her in on this phone call. But she's written a book that comes out next week called Black Hole Survival Guide. I'm showing it on the screen here. So it could be very practical. We'll ask her when she comes on how long it will take and what she will do on the way down. But please continue.
Oh, she's been looking at that. That's nice.
Yes.
Yeah, no, you have quite a bit of time. You could certainly do a lot of observations as you fall. You couldn't communicate with your friends outside.
Yeah, you won't publish it, but
no, that wouldn't be much good. No. But no, unless you see there were wormholes, and then of course you have to violate energy and all that sort of stuff. But never mind. No, it doesn't matter that much in a sense, except as you said it before. Why do we need to know? Is it just we like to know what's happening because we like to know what's happening, not because it's any use to us? Well, I guess that applies to lots of things in astrophysics and so on. You might see what was it recently? A magneton, was it?
Yes.
just the other day, somebody that's good fun, and you might work it out and so on, but you're not likely to go and see it. No, the point is a different one, which I hadn't really got down to. The argument I'm making is that we need a theory which combines general relativity and quantum mechanics, and that we really need if we want a coherent description of the world in many ways. We need that theory which combines general relativity and quantum mechanics, but it won't be what people think of as a quantum gravity theory, that it's not quantum mechanics which rules. It's they both have to rule in some kind of union. The thing is that the problem with quantum mechanics, as I was trying to say, is this reduction of the state or collapse of the wave function, whatever you want to call it, which seems to go against unitarity. They go against the Schrödinger equation. You have to have something else. And either you have to go, there's sort of routes that people take. Maybe it's consciousness, which has different laws. I'm sure that doesn't resolve the measurement problem. You could imagine, for example, some distant planet, on which there is an atmosphere, something like the Earth's atmosphere. And we know about things like butterfly effects, that the actual atmosphere depends on tiny little effects. It's a chaotic system. And it depends ultimately probably on quantum effects. Mm-hmm. Now, you see this space probe is going out to this distance, several light years away, and it wants to take a photograph of the atmosphere of this planet. Now, there's no life on that planet. It's an Earth-like planet, but there's no life on it. So there are no butterflies. Well, there could be butterflies, but there are no conscious observers. And so, according to the consciousness that reduces the state theory, the atmosphere will be some complete quantum mess of superpositions of different atmospheres. Just a whoosh. Okay, the probe sends this pictures of this whoosh back to the Earth, and it takes a few light years, and then somebody is sitting in front of a computer screen looking at this whoosh. As soon as the picture comes on the computer screen, because that's a conscious being looking at it, suddenly it reduces into one atmosphere or another. This to me is complete absurdity, even more absurd than Schrödinger's cat. It's telling us that there is something wrong with the view that it's consciousness that reduces the state. So I don't think it's that. I do, however, have this crazy view that it could be the other way around, that whatever is involved in the state reduction, which I believe to be a physical process which is going around all over around us, the state is being reduced all over the place. It's reduced when you get enough mass displacement. So it's not just a dead cat and a live cat. You have two configurations which differ sufficiently. It doesn't have to be very much. And you can see how much it is from the calculation. It doesn't have to be very much. And then it reduces to one or the other. Mm. So this reduction is a physical process which takes place spontaneously. There doesn't have to be any conscious being looking at it or even anywhere close. It just does it itself, according to some law which involves both gravity and quantum mechanics, which we don't have yet. Although it's possible to make estimates using principles of general relativity, mainly the principle of equivalence, which is the principle of Galileo and Einstein, that free fall cancels out gravity. So the rocks falling from the Leaning Tower of Pisa, if they ever were, would fall together as though there were no gravity. And Galileo gives a wonderful description of fireworks. You see a fireworks goes up and you see this beautiful spherical thing falling just as though there was no gravity. And he uses this description in his books. I find that really wonderful.
Yeah.
So you well appreciated that you could cancel gravity out by falling freely. Mm-hmm. And then Einstein takes this further to say, yes, this is a fundamental principle. Gravity is not a force. It's something more subtle than that. You can cancel it out locally. What's interesting is how that force varies from place to place. And this is where you get into the Weyl curvature. The Weyl curvature tells you one of the ways in which it can vary as you move from place to place. So, now, what I'm saying is that this principle is inconsistent with the principles of quantum mechanics. You can do a little calculation, and you can see that if you take the principle of equivalence, it is inconsistent with the normal principles of quantum field theory. That if you can cancel a gravitational field with free fall, then it gives you a different vacuum from you do if you don't free fall. And this gives you, if you have different free falls in different places, you have a problem with quantum field theory. And you can estimate how big that problem is, and that gives an estimate of how quickly a quantum state will reduce in terms of how much mass you've displaced between the two states.
And the Weyl curvature is a purely classical object, correct?
Yeah. Yes.
Mm-hmm.
Yes.
And so how does it play a role? Maybe we can move to talking about, I want to finish this discussion of black holes and especially of what happens with the so-called Hawking radiation that will eventually become important when we talk about when we talk about conformal cyclic cosmology. Can I get from you how did you react when Stephen came to you and when you learned about Hawking radiation? This was in 1970. So how did you react? Did you say, "I wish I thought of that"?
No, it was more like this. I can tell you the story. No, I simply heard, what was it? Whether I'd heard a rumor. I think I phoned up Dennis. I can't remember. I think I'd been away somewhere, and I called Dennis up, and I said, "What's new?" I can't remember exactly what it was. He said, "What's new?" And he said, "Oh, have you heard? There's the Stephen Hawking tells you that black holes actually radiate and so on." And I said, "What?" And so I phoned Stephen up, and I phoned him up, and he described it to me. And it was, I think there were two questions. One is, I asked what happens to the black hole because the radius can't get smaller without negative energy. So he said, well, in quantum field theory, you can violate the energy conditions, which I knew already. So I said, oh, I see, it's that. Okay. But then he said, I can't remember in which order, but then he said, it's very good to have to have a temperature attached to black hole, because that makes sense of the formula that Stephen and Brandon Carter and Jim Bardeen, I think it was just three of them, there may have been another author, had written a paper in the analogies between black hole dynamics and thermodynamics. And you had one thing corresponds to this thing, and the thing that was missing in this analogy was the temperature. You see, everybody thought black holes didn't have any temperature. They have to be absolutely cold. And I didn't know to be worried by that. So I think I did think the entropy did apply to the black hole. But Stephen thought it was merely an analogy. And then until he did his calculation to show that there was a temperature, and therefore it wasn't just an analogy, it could be real. And so then he told me this, it fits in with the formula. I'd say, okay, that's fine. So no, I was convinced already in that phone conversation. But I hadn't thought of it. No, I thought if you make sense of the thermodynamic analogy, which I really believed already, that the temperature had to be there. I hadn't predicted it at all. So I was surprised by it. But in view of this conversation, I was happy with it. Reasonably.
And what do you make of the connection between black holes and the origin of the universe as we turn towards conformal cyclic cosmology now? I want to get your opinion about how it is possible that such, two completely different on the face of it events and so forth or phenomena have at their core potentially interwoven aspects. And even in the case of both Hawking radiation and conformal cyclic cosmology, they have much to say about not only the beginning of the universe potentially, but the end of the universe in terms of what will remain many eons from now. So why is it that a black hole would play a role in the future of the entirety of our universe?
Well, you see, I remember thinking how boring the universe is going to be, you see, because, okay, you get these black holes, they're pretty exciting for a bit, but then you get rather bored with them after a while. They swallow entire galactic clusters. That's the likely thing. Superclusters will disperse from each other, but individual clusters will ultimately be swallowed by, various black holes, and they swallow each other, you see, and then there's some final king of black holes, which just sits there, and it sits there, and it sits there. Now, that's pretty damn boring. But what's really boring is you have to wait for, something like, I guess Don Page told me, 10 to the 103 years or so, more than a Google year, 1,000 Google years or something. You have to wait till the biggest of these black holes finally decide to evaporate away completely and disappear with a pop. Something like that. And then it's dead boring, absolutely dead boring. So I thought, gosh, this is boring. And then I thought, well, who's going to be bored by this? Mostly photons, they're just photons running around. And it's very hard to bore a photon, not simply because photons don't have any experiences, but because the time from the creation of any photon until infinity is nothing. People often argue it the same way. They say time freezes or something. It's the wrong way around. time flips by as though it's nothing. So there is no time experience at all for that photon. The entire universe flashes by until it gets to infinity and goes through to the other side. Now, why do I say goes through to the other side? Because in the early days, when I say the early days, in the 1960s, where people were playing around with gravitational radiation and trying to work out how you work out the energy carried away in gravitational waves and so on, Bondi and Sachs and people had wonderful formulae for this. And I said, I thought of a better way of looking at it from my point of view. You take a conformal map and you squash infinity down to a sort of boundary. Now, what is a conformal map? Well, I think a very good illustration of this is one of these Escher pictures. There's a famous one called, I think it's circle limit 4.
Yes, I'm showing that. Yeah, I'm showing that on the screen for our listeners.
The angels and the devils.
Yes, the angels, the devils, and the three-dimensional model that you have of it in the book.
Yeah, that's 3 of them.
I'll show that. Yes, go on, Sir Roger.
3 different geometries you can have for
there they are.
Uniform two-dimensional surface. Well, take the circle limit. That's the angels and devils. Seeming to crowd themselves more and more together towards the edge of the picture. Now, as far as these angels and devils are concerned, you have to imagine that their geometry, they're not getting squashed towards the edge. They're the same size and shape as the ones in the middle. And this is a conformal representation, which means angles are correctly depicted right up towards the edge. So if you looked at the angle on the devil's wing, say, that would be exactly the same as close as you could get to the edge. Or the shape of the devil's eye, pretty well, is the same, right? Small shapes are correctly represented. Even though they look smaller, what's called the conformal. Oh, we've run out of time. So we have
no. It's I have just have Jana Levin on the line. I'm trying to bring her in. Jana, can you hear us?
My screen has gone blank.
Oh, no.
Is that right?
Can you see me?
I can see you in the corner, but not in the main screen.
Oh, it's okay. I still see you. Trying to ring Jana Levin here to get her on. Jana, are you there? I can't see you. I can't hear you. Let me keep going. Actually, Sir Roger, while I'm working on this, can you hear me?
I can hear you, but you're small.
Oh, okay. Yeah, don't worry about my size for a second. Yeah, I see you. Yeah. Okay, so Jana's here now. There's a question that I find really interesting from a listener named Church of Entropy. The question is it possible, I'll read you the question, how is it possible to have a universe with singularities that also has the ability to make conformal mappings? Don't they exclude, doesn't the existence of even a singularity preclude the existence of conformal mappings?
No, let me, I don't know if I can get your picture back because it somehow has disappeared.
Let me see. Hold on, does this work? Can you see me now?
No.
Roger, do you see me at all? If you click on the picture, do you hear me?
If I click on the little picture?
Yeah, if you click on the little picture, it should make it bigger.
I think it got bigger, but then it went small again. No, it wasn't you.
Let's see. Okay, I can still hear you and I can see you, so I think that's... Yeah, I think that's the important thing. If as long as you can see me, I can see you. Even if it's small, don't worry about it being small, Roger. That's not important.
Yes, I think you're looking awfully small. That's all it is. Yeah.
Okay. Yeah. Don't worry about that.
Yes. Singularities. Well, you see, conformal geometry is actually something I used to be interested in. I think I played around with it when I was an undergraduate, even before maybe. You can think of it in the plane. You see, in the plane, you think of projective geometry. The straight line is the dominant thing. And if you think of a picture, you project a figure onto a plane, and straight lines remain straight lines. That's projective geometry. Now, conformal geometry is something where angles are preserved, and you can have conformal geometry.
Uh-oh, Jana. I think I lost Sir Roger. Let me see. Everybody, please bear with us as we're trying to get Sir Roger connected with Jan 11. Hopefully, he will pick up the phone, the Skype call. For now, just to remind you to download the slides in the link in the comment section. I left the link there. Let's see if I can get him back on. Try to get too complicated here. It'll probably just be a minute. He's quite good at technology, especially for a theorist. Let's see if he'll come back on. So we will continue because I want to get to the conformal cyclic cosmology, and hopefully that will work. Let me switch back. All right, now it's saying call him when he gets back. Let me try to reconnect him. I know he's still there. I do know he has to reconnect. Let's see if that will work. Hopefully his computer is still working. Roger passed the event horizon. Hopefully not, because that would mean he wouldn't come back. If he doesn't pick up, I'll try him by email one more time. For some reason, I think he's gotten kicked off. Let me try one more time here. See if this works. Yes. Hopefully he'll cyclically return through the magic of Skype. All right, I'm trying to text him now. Bear with me here. Okay, I'm ringing him. Should be there. Try one more chance here. See, now I'm frozen. That's not good. Can people hear me still out in the stream? Can people still hear me? Let me know if you can hear me out there in the stream. Could be a quantum fluctuation. Very good one. He cycled out of the universe. That's a good question. Can you guys hear me on the stream? If not, let me know. Yes, you guys can hear me. Okay. Good. Let's see if I can get him back on. Oh, maybe there we go. Roger.
Yes.
Can you hear me?
I can hear you all right.
And Jen, are you there too?
Yeah.
Wow.
I can hear Roger and I can see Roger. I can't see you anymore, Brian.
You can't see me? Okay, don't worry. I'm not so important. Hi, guys. It's great to have you here. So, yeah, now we can all hear it. Do you guys hear us on the internet still on YouTube? This is just for YouTube question. Do you guys have it on YouTube?
Yeah. You see, the important thing is that if you have full relativity, you have clocks to measure times and therefore distances. You send a light signal back and forth and you can measure a distance that way. So you have accurate clocks. And this comes about because you have mass. Now the opposite side to this is if you have a state of the world where you don't have mass, and in the very, very remote future, all the black holes have evaporated away, and you've just got photons, basically photons. You've got some other things too, but let's forget them. Essentially photons running around. They don't have any mass, and therefore the geometry that they respect is conformal geometry, where you can stretch and squash as long as the stretch is uniform. You have to stretch as much this way as that way, and you have to stretch the time by the same amount as you stretch the space. So the light cones remain there, just as they were. Now, this kind of geometry is the geometry of the physics of masslessness. And in the very remote future, the argument goes, you have massless physics. Maxwell's equations, which describe electromagnetism and photons, if you like, they are completely invariant under squashing and stretching. You can squash in one place, stretch in another place. Maxwell's equations don't even know anything's happened. This applies to massless things. Now, what about the Big Bang? It's just the same, but for the opposite reason. There you have enormous energies, things swishing around at enormous speed. And there, the kinetic energy of particles completely dominates the mass. So although they do have mass, the particles in the very early universe, the mass, the closer you get to the Big Bang, the more and more irrelevant the mass becomes. And you have a massless physics. Right as you go in the limit back into the Big Bang, again, you have massless physics. So my argument is that in those two regions, the dominant physics of the universe, or the dominant geometry of the universe, is conformal geometry and physics of massless things. So the remote future is massless because it's got all that rarefied and basically photons. And the Big Bang, where you have basically massless entities again, the physics is very, very similar. It looks completely different because in one case, the Big Bang, you've got enormous densities and enormous temperatures. In the remote future, you have ridiculously small densities and very, very cold. Very hot in the Big Bang, very cold in the remote future. But if you do the squashing, the geometric squashing in the future and the geometric stretching of the Big Bang, the temperature goes up when you squash the future, the temperature goes down when you stretch the Big Bang, and there is a match. It looks as though they could easily match. And the argument here is that they do match. So it's a hypothesis that if you squash down the remote future, you get something looking like another Big Bang. So the picture I have is one where you think it more like a cylinder. You have the Big Bang stretched out and the infinity squashed down, and then you can join that cylinder onto another one, have another one before, so that our Big Bang was the conformal continuation of the remote future of a previous eon, I'm calling it. So I say our eon is Big Bang to remote future. The next eon will have our remote future as its Big Bang. Our Big Bang was the remote future of one eon. Its Big Bang was the remote future of another one, and so on. Now, I used to go around giving lectures on this, feeling fairly satisfied. Nobody will ever be able to disprove it, so I can go on forever giving these talks. And then, irritatingly, I had an idea. The idea was, when you consider the black holes before they've evaporated away, particularly ones which cohabit a cluster of galaxies, our own black hole, which just got the Nobel Prize as well for the two other people who shared the Nobel Prize for amazing observations, which I was most impressed with when I saw them, which you see these stars going around this invisible central object, and you see they're going these wonderful orbits. I thought, gosh, Kepler was right. Well, almost, because you see these elliptical orbits going around and around, all over different planes and so on, and there's this thing in the middle, pulling them around in these orbits. Wonderful. And so there's evidence for something like a 4 million solar mass black hole in the center, worth the Nobel Prize, which it got. But anyway, these black holes gradually gulp down pretty well. I don't know what proportion of the stars in the galaxy they swallow, but probably most of the stars in the
millions, right, Shannon? What's the mass at the center? Is it 4 million?
Yeah, it's 4 million for Sagittarius A star. And but the one that we took the picture of in M87 is more in the billions of times the mass of the sun, much, much bigger. But because it's 55 million light years away, it actually subtends about the same size on the sky for the telescope as our smaller black hole does. That's 26,000 light years away, which is to say much closer. So it's bigger and further, but was the only other target for the Event Horizon Telescope project. And I think that was the only big surprise at the reveal. I went to the National Press Club to see the reveal. I was so excited.
Oh, wow.
And they had 3 badges: scientist, journalist, and like friend, and I think I took all three. And so for me, that was the big surprise, was that it was M87 that they took the picture of, not Sagittarius A star.
Right.
So we're still in pursuit of an image of our own black hole.
Now, when we look at showing the cover of your book now, the Black Hole Survival Guide coming out on Tuesday, I'm excited to be discussing that with you this coming Tuesday.
Looking forward to that.
So we had a question for you earlier. The astronaut who's on the cover, I presume that's you, right? That person who is falling in on the cover. The question is, what is the nature of the time and the experience for such a person? Obviously, they might survive where they're pictured, just on the outside of the event horizon. But how long will it take for this astronaut, this comely astronaut, to get to his or her ultimate doom?
Right. So the trick of surviving a black hole for as long as possible is to fall into as big a black hole as possible, which seems counterintuitive to people. You would imagine a bigger black hole is stronger gravitational field, that it would be worse. But actually, you notice the curvature less. So imagine you're standing on a basketball. Your 2 feet are very aware that you're struggling because they're in different points on the curvature of the black hole, of the basketball. But if you're standing on the Earth, you don't really notice, right? Your feet feel like they're level, like they're flat. And so the same concept with a very big black hole, you could sail across the event horizon very comfortably. You could still be vigorous with youth when you cross the event horizon. You would hardly notice that you had done so. There wouldn't really be an obvious experience that would let you know that you had crossed the event horizon. So that's one of the beautiful ideas that Einstein came up with, which was the equivalence principle. And it has to do with the fact that if space-time is gently curved, it should look like space-time in flat, empty space. But once you cross the event horizon, then you have a very short order before you hit the singularity. And I'm sorry I missed some of the previous conversations, so I'm not sure if Sir Roger talked about this, but part of the Nobel Prize winning work was to prove that, at least in the context of general relativity, the formation of the singularity was inevitable. And not only that, and I saw you showed some of those light cone pictures, it's in your future, right? So the singularity is unavoidable once you've crossed. You can no more avoid it than you can avoid a future moment in time. And in a black hole around the size of our sun, which would be a very, very small black hole, you have much less than a second to survive before you get into real trouble. If you make the black hole as big as M87, like 6 billion times the mass of the sun, something like that, you have that much longer to live, 6 million times longer to live. You might even be able to eke out a year if you made the black hole tens of billions of times the mass of the sun. So you would have a very existentially fraught year as you encounter, knew inevitably that the singularity was in your future. And there might even be some trajectories you could rig where you got a little bit longer out of it. But destruction is inevitable.
And Jana, I want to thank you so much for the discussion. We're joined now by another special guest. Sir Eric Weinstein is joining us from somewhere in the Ethernet. Eric, you're looking sharp. Say hello to Jana Levin, your friend Jana Levin and mine. And Jana, I'm going to, yes, you can jump off, Jana. I wanted to say, Eric, tune in Tuesday. We're going to have 2 live streams with Jana, one at 9 in the morning or 10 in the morning Pacific, at 1 p.m. Eastern. We're going to discuss the entirety of this wonderful new book, Black Hole Survival Guide. Thank you, Jana. Have a wonderful weekend.
So much. Brian, thanks for doing this. Eric, great to see you if briefly. And Sir Roger, I miss you already. Last time I saw you was last December, and it was lovely. So be well, everyone. Thanks for having me on.
Bye, Jana.
Bye.
Bye-bye.
So, Eric, let me get you included here. You are on live on screen with Sir Roger Penrose. I can't hear you, Eric. Can you? Are you muted?
I think he's muted.
I think you're muted, Eric. I can't hear you. I can hear. Let me see.
Okay.
There we are. Hello, Eric.
Roger, great to see you again. Wanted to first of all just say mazel tov on getting the recognition. It's great to see top level theory back in the game, and just wanted to wish you all the best in mazel tov.
I appreciate that. Thank you.
So, Eric, we're going to be talking in a minute about Roger's conformal cyclic cosmology. We just had a very riveting discussion about the Weil curvature hypothesis and whether or not we even need a theory of everything, whether or not we even have reason to believe that there are singularities in space-time. I said to Roger, the only instances they appear are forever shrouded from our view, either in the deep ancient past of the universe, at the origin of the universe, our current cycle of the universe, if you will, or perhaps hidden at the core of black holes, forever inaccessible, as Jana points out in her book. What say you? Are singularities real? Are we just kind of fooling ourselves? And if they're not real, why do we need a theory of quantum gravity?
Well, the first thing I would say is why waste that question on me with Roger around? So let's spin it towards Roger.
I want to hear you guys converse about it. Yeah. So I asked Roger. I got his opinion, but I'm not going to tell you what it was because I don't want to prejudice your opinion.
Right.
I know how influential Roger is on you, and I know how susceptible you are to peer pressure.
Okay. Well, this is like going into a dojo and finding Anderson Silva wants to spar or something like that. Okay. So here we go.
Yeah.
I guess what my read on it, and in part your work, sir, is that this is the key to understanding that Einstein is really only an effective theory, because I don't believe that those singularities will be there in an ultimate theory. And the fact that they're shrouded by mystery and that they're sort of protected so that we sort of can prove that they have to be there at this level of theory, but on the other hand, we can't really get at them because they are, in fact, screened from us in one way or the other for these two different types of singularities. Is this, sir, the indication that Einstein must be effective, or could it be, in some sense, an ultimate theory in that sector with these singularities, essential features of space-time itself? Is this an artifact of our description, or is this, in fact, how the underlying structure likely is, in your opinion? And if I need to rephrase the question, and I'd love to get back to the Weil tensor, but that would be the opening.
Yeah. Sorry, do you want me to say something?
Yeah.
I mean, I guess it's, you see, when I first wrote my papers on this, I don't think I tended to use the word singularity. It's just we don't know what happens at that point. Stephen Hawking was more bold about using the word singularity. I think he meant, okay, as far as the classical theory is concerned, we have a singularity, so it gives up at that point. I mean, like with the shock wave, you might say the theory of laminar flow or whatever it is, and aerodynamics gives up, and you have to have another theory which describes the shock wave. So the argument would be something like that. So general relativity, as we know it, would not apply to what happens. But whether there's any useful future to the situation, you see, you might say the very notion of your space-time and what it means to talk about the future makes no sense at that point. So in the absence of any theory, it's telling us that our theory of space-time, general relativity, gives up at that point. It doesn't tell us if anything happens. I mean, what does it mean? Anything you took into that region might get destroyed, and then doesn't mean anything to say it continues. You see, this was an argument Stephen made, which I would have agreed with, you see. Here's the narrative, you see. I would have agreed with this argument. The Big Bang, you see, was the beginning. You may say what was before the Big Bang. Well, it's meaningless to talk about what was before, because the very notion of before is a space-time notion, and therefore it doesn't make any sense to talk about before the Big Bang. And I would have said, yeah, I agree with that. And here am I contradicting myself. See, if you've got a theory, then you can maybe go beyond what you had before. So I don't agree with the argument that it's meaningless to talk about before the Big Bang. I better not, because I'm talking about it. Yes.
So, Eric, both of you guys have had, controversial but provocative new theories that push the boundaries of the accepted dogma. I think in many circles, Sir Roger is sort of a hero or precursor to some of the work that you're trying to do now. Certainly he is for me. I want to turn to his conformal cyclic cosmology, which is my area of expertise, such as it is. and talk about, well, first of all, what's it like to be on the avant-garde of physics in a good way, to work without a tightrope, to pursue things that may not have answers. What does that feel like for you, and what kind of inspiration do you take personally from someone like Sir Roger?
Well, I mean, first of all, Roger is oddly, of course, singular in our pantheon of living physics heroes as being, I would say, almost everyone would say, the most generative of our first rank of physicists. So that he is less constrained, because in some sense we're in such a late stage of physics that almost every interesting idea is dead on arrival. And so having any ideas at all that aren't immediately dead on arrival is very, very difficult. And I think that one of the things that this Nobel Prize is going to do is to send a message to future generations that it's okay to be highly generative. You just have to do it in a radical and conservative fashion simultaneously, so that the math is extremely, it's impeccable stuff. And on the other hand, it's also wild stuff. I remember seeing the newsletters from the Twister group back before the internet. And this was like samizdat. We weren't sure whether people were taking drugs in Oxford or what was going on, but it was florid, and it was in its own language, and it was clearly shared by a group of people. And I just think you have to think about Roger Penrose as like Sun Ra, the great jazz artist who had a cult and a commune in his house, but also produced some of the best music around. This is really a throwback to that tradition. It says that it's possible that Roger could have done this if he wasn't at Oxford as well. I would say the one thing that I want to be really clear about is also bringing back hardcore geometry rather than always coming back to the quantum as the source of weirdness. I think one of the things Roger has done through his artistry and his ability to depict what can barely be seen is to show us the wonder of geometry that is now underneath all fundamental physics, as post Jim Simon's work with C and Yang. And so right now we're living in a world that's purely geometric, in which most of the public discussion of physical weirdness is about the quantum. And so I think Roger renewed that Einsteinian connection and the sort of Simon's Yang connection by making this relevant. But I would like to get off a technical question just while I've got.
Of course, go for it.
You talk a lot about the Weyl curvature tensor, which is the part that gets killed when we write down the Einstein field equations. It's the part of the curvature that's sort of thrown away with the bones and the skin when we formulate the Einstein field equation. On the other hand, it's also weirdly the part of the curvature, as per the Chern-Weil theory, that contains most of the topological information about the nature of the space on which it resides. What do you make of the fact that we throw away the portion of curvature that tells us about the holedness and the donutedness of potentially of space-time, but we retain the portion that is complementary to that when we write down the Einstein field equations? Is that a coincidence? Does it have greater significance?
I'm not sure I'm answering your question, but the way I would look at it is not in this respect too different from electromagnetism, because there one has the Maxwell field and you have the charged sources. So in general relativity, the analogy, according to me, it wasn't perhaps the way other people would look at it, but according to the way I would look at it, you see that the Weyl curvature is very analogous to the Maxwell field. And when you write it in spinors, it's almost just the same equation you write down. So it's the Weyl curvature is an analog of the electromagnetic field, and the Ricci curvature is the analog of the charge. So you see you have matter with charged matter, and that gives you the source to the Maxwell field. And here we have the Ricci tensor, which gives you the source to the Weyl field. So it's not so different in that respect. I think I'm looking at it a bit differently from the way you are.
Well, it's interesting because because the Maxwell theory doesn't break into pieces, whereas the Riemannian or Einstein theory does break the curvature into pieces. Yes. I don't think I've ever heard that.
It's a question of order of differentiation, you see. Yeah, I mean, there is a different order of differentiation, because when you write down the Maxwell field and the charge, there's a different level. But in the Einstein theory, the Ricci and Weyl curvature are at the same level. You see, people think of them as the curvature tensor. I think it was when I wrote these things in terms of a spinor form, which made these things look more different. See, the Weyl curvature looks, just 4 indices rather than 2, but it looks awfully like a Maxwell field.
No, I quite agree with you about putting these curvatures together. While Brian is distracted, I can actually take over his podcast and ask you a few more questions if you don't mind. One question I was curious about is that in low dimensions, close to where we are and close to the signature in which we're in, which is 1 dimension of time and 3 of space, there are lots of weird coincidences. We have a mass possibility in 2 spatial and 1 temporal dimensions called topological mass that's not available anywhere else, again, partially due to Jim Simons, but this time with Chern. We've got this Cotton tensor that replaces the Weyl tensor in some ways in dimension 3. We've got self-dual equations in dimension 4, but you'd have to have 2 dimensions of time and 2 of space. So we have all of these weird just miss opportunities for our 4 dimensions, 3 of space and 1 of time, and we're surrounded by exotica. There are platypus and echidna everywhere, and weirdly, we're always just out of reach of their weirdness to power our universe. We could have used topological mass maybe rather than the Higgs mechanism if we were 1 spatial dimension lower. Do these practical jokes suggest to you that they are of any real importance, or are they merely sort of distractions in a perverse creator's sense of humor meant to waste our time and get our hopes up only to dash them to the ground?
I think it's a very subtle question. You see, you have these echidna.
By the way, I'm going to take a victory lap.
Like that. Yeah, you got a platypus in there. You got a whole host of oddities in the orrery of Eric Weinstein. Go on, Sir Roger. Sorry.
What the plural of a platypus is it platypi or is it platypus?
That's hard. If you could figure that out, you'll win the Nobel Prize in physiology.
This turns out to be octopodes.
Octopodes. Well, I think an octopus I thought it was perfectly legitimate to call them octopuses.
Yeah, I think it is legitimate, but the top drawer way of pissing everyone off is to say octopodes.
Octopodes.
I was pronouncing as octopodes for years, but please, sir, continue.
And this is an echidna. Well, an echidnae. No, I don't know. You see, I have no idea. But anyway, I was told that if you don't know enough Latin or Greek or whatever it is, you can always use the English way and put S on the end. Anyway, so yeah, I mean, you've got these strange creatures, and you have strange creatures in different dimensions. And the trouble is, if you're a mathematician, as I accompany a lot of people who are doing the mathematics, twisted theory is a good example. You see, you do it on the wrong signature, in my view, and you get all sorts of beautiful things, and they prove wonderful theorems and all sorts of stuff. And you can take more dimensions too, and you can do things like this, and you can play around with this, or you can do what Ed Witten did, is change the signature the other way around, and take 2 pluses and 2 minuses, and then your twisted theory becomes real, and so on. Okay, it might be a nice trick to play around with for a bit, but it's not physics. Physics is the Lorentzian signature. And I've always tried to gear what I've done to what physics is doing more, and try to not get too pulled away by mathematical things, which may be very beautiful and elegant, and they do amazing things in all sorts of different ways. But are they connected with physics deeply? Not necessarily. There are a lot of traps, you see, that you can go guided off in all sorts of different directions mathematically. And how connected with the physical world are they? I don't know. I mean, they might be in some way. I mean, spinors, you take spinors, and if it's in Lorentzian, they have a particular personality when you're in Lorentzian space-time. When you go to 26 dimensions, they're horrendous. So where do you go, and do you study? Well, you study things that have a beauty in n dimensions, but it's not the same thing.
But there's certain things in 24 dimensions or 7, like there's a vector cross product in 7 dimensions. It doesn't feel like we're very close to it. Yes. So I don't think it tempts us. It's a very weird thing to know about why 7 dimensions would have a vector cross product. But the fact that we're so close to these 3 and 4 dimensional coincidences is feels very different to me than, let's say, the Leech lattice or particular results in 26 dimensions, which are really dimensions 24 results having to do with supersymmetry and things like this.
Yes. Well, I don't know. I mean, mathematics is full of coincidences, and they may or may not have anything to do with physics.
So you're agnostic in some sense.
Yes, yes, definitely. I would say most of them don't seem to have much to do with it. I think they may, in some deeper, remote physics that we come to eventually, we'll see, oh, that's what that's for, you see.
Well, and then one of the things that I find fascinating about your work is that you really come across to me as someone trained as a mathematician who actually has accepted the yoke of physics, which in some sense is a very weird thing, because most people who appreciate the beauty of mathematics find the idea that one particular physical world should draw our attention to be kind of coercive, imprisoning. It feels artificially small. Whereas from the physics side, most people who really want to keep themselves wedded to the world in which we live train themselves to resist the siren song of beautiful mathematics.
Yeah.
Why are there so few people in this interesting little overlap between them who are really concerned about the physical world and the most beautiful mathematics, which oddly the physical world seems to know very well?
I don't know that I can answer that question, but you're right. It is a puzzling thing. Well, I mean, you see, when I was doing my mathematics course, I did an undergraduate in mathematics. Of course, in the UK, that includes a bit of applied mathematics. So I did know about Lagrange equations and that sort of stuff.
It's been funny, Sir Roger, to see the response on the internet. Reminds me of a quote by, again, your fellow laureate, Albert Einstein, who said that if my theory of relativity proves to be correct, Germany will claim me as a German, and France will claim me as a citizen of the world. However, if it proves wrong, France will say I'm German, and Germany will say I'm a Jew. And it reminded me of, you made a quote the other day that said something like, to the mathematicians, I'm a physicist, and to the physicists, I'm a mathematician. It was kind of rhyming with that. And I wonder if an alien wakes Sir Roger up at 3 a.m, you've done all this different work in math and physics and quantum mechanics and consciousness and black holes and singularities and
Art.
What's that?
Art,
and yep, absolutely. If this alien comes from another planet, and first of all, do you believe aliens exist? And second of all, what do you define yourself to that alien?
Aliens? Oh, I see. Do I believe?
First, do you believe in aliens? And second, if they do exist and they wake you up, what are you? A mathematician, a physicist, an artist, a scientist? Yes.
Oh, right. I mean, I get away with it by saying I'm a mathematical physicist, but that's cheating. Where is my soul, I suppose you might ask.
Yes.
Is that the sort of
what is closest to your heart?
Very difficult question, because of beauty in the mathematics. But you see, it's a hard question. No, I was going to say when I was an undergraduate, the thing that completely bowled me over was complex analysis. You know, it's the way they teach it. They first teach real analysis, and they go, C0 functions, C1 functions, 317 functions, C infinity, C omega functions, C infinity functions, and they're all different. And then you do complex analysis once there is differentiable, and the whole lot there in front of your face. Complex analysis, you contour integrals, amazing, and all that stuff. And I thought, before I knew much physics, I thought, gosh, wouldn't it be amazing if the physical world was really driven by this wonderful structure? And I had a lot of kind of internal conflict between complex numbers and combinatorial physics, as I used to be equally attracted by both ideas. But I think the complex analysis won in the end. It's just the magic in it, I guess.
What about higher spaces? Complex, if a complex appeals to you, I've got these things called quaternions. If quaternions appeal to you, I've got these octonions. And then Eric always loves to go on about Clifford algebras, etc. Is there a limit? Is there some place where the fascination stops for you when it comes to the bewitching power of mathematics in the physical world?
It's where these two sides to me having their battle, and the physics side probably wins. Because, I mean, the beauty lies on the mathematics side, but the what would I say, the drive comes from the side.
When Eric was on my show, we talked about how physics, classical, not classical physics, but classical approach to solving theoretical problems seems to have stalled in some sense with breakthroughs like yours coming, before either Eric or I were born in the 60s. Are we stagnating in theoretical? I should say, are you guys stagnating in theoretical? I'm just a simple experimentalist, so I take no blame.
So when you mention octonians, I think the split octonians probably do have fundamental.
Oh, really?
Split.
Uh-huh. What are the split octonians? Can you describe that, either one of you?
Well, you see, octonians, you've got 8 generators, mm-hmm. and you don't have a positive. You have a well, think of quaternions first. You've got a norm, which is the sum of the squares, mm-hmm. and you have a similar thing for octonians. Mm. The split quaternions, you would have 2 pluses and 2 minuses. Let me just think. Split octonians, basically it's like you have quaternion. You have proper quaternions in them, but you can find subsystems which are genuine quaternions. Mm. So this is all to do with twistor theory and palatial twistor theory.
I see.
You've got these algebras, and you've got the subalgebras, which looks to me as though they're going to be things like these. Certainly the quaternions. Mm-hmm. I think split octonians have a role to play. You see, it's to do with the signature you get on twistors. You see, you've got this form, which is a Hermitian form, which has 2 pluses and 2 minuses. When you write that as a real form, you've got 4 pluses and 4 minuses. And you can think of that as an 8-dimensional vector space. And I think the split octonians have a role to play there. But it's something I might change my mind about.
So I have a question from a listener, Miguel, goes by Yeti Tears, a good friend of Eric's and mine. Eric, and Miguel is wondering, Sir Roger Penrose, what is the initial inspiration for your drawings, your tilings, your mercurial sketches that are so mesmerizing? What question do you ask yourself before you sit down to do art? What do you ask yourself?
Well, there's all sorts of things. I think if you look at my old notebooks, you find it's full of these drawings. And mostly they are where I couldn't think. I got stuck, you see, and so I just draw wild things. They're very wild. Mm-hmm. So I came from my grandfather on my father's side was a professional art painter.
Yes,
he was a very good artist, and my father was one of 4 brothers, all of them who were distinguished. They were very good artists. My father was a very good artist. But his younger brother, Roland, became a big figure in the Surrealist movement. So he was in with all the, Picasso and Max Ernst and various people. And he also was one of the originators of the Institute for Contemporary Arts in Britain. He started it. And, but my father's interest in art was much more, what would you say, conservative. He liked to draw realistic views and things. So I departed from that myself. I would draw wild things. Sometimes I draw realistic things. So it's not uniquely that.
Very interesting. So,
Roger, I'm curious.
Yeah, Eric, go ahead.
You come from a family, sir, of eccentrics and geniuses and incredibly interesting tree. Do you believe that tree really is intrinsically, in some sense, tied to the UK with its tolerance for people who weirdly either conform or wildly don't conform? That there's a sort of a weird way in which you can be British and be respectable and totally non-respectable at the same time. There's some special sauce.
I think you're right. There is something there. That's right. Certain Britain, there is a sort of kind of snobbish, very conservative, whatever the word is. But then a respect for being outrageous in one way or another. Yes, I think there is, and being there's an obvious word that's just slipped out of my mind here.
I think outrageous is pretty good, Brian. He said it, I didn't.
I was going to go with iconoclastic and courageous, but yes.
Outrageous is much better.
I mean, there is a respect for that in Britain, which I don't think you get so much of that in the States. At least, I don't know if it's true now. but it hadn't been perhaps so much in the past.
We're trying to get Elon Musk to behave so he'll stop getting those rockets land successfully and stop making these beautiful products.
Yes.
So, Sir Roger, I can't help but ask, from the personal side, how do you think of Stephen now? How do you think his legacy is affected by your Nobel Prizes? Eric, my friend, always says there are Nobel Prizes that give prestige to the victor, to the one who wins it, and then there are victors who give prestige to the Nobel Prize. I think, Eric, you would agree with me that the latter is true for Sir Roger.
Dude, you can't do that. He's right here. You can hear everything.
I know that. That's right. Well, man, he will indulge me. I told him, he endorsed my book, Losing the Nobel Prize, and it could have cost him his Nobel Prize. If they were smart, they wouldn't have.
It was a shoe that pushed you down, and he ascended in the same motion.
So, Sir Roger, how would Stephen have reacted? First of all, do you think that he should have shared in this prize? I mean, this rule that only 3 people can win it is so antiquated and ridiculous. And clearly, he deserved it in a large sense, according to a lot of people. Where do you come down on that?
It's a difficult one. You see, he always thought that if the Hawking evaporation for small, little tiny black holes had been observed, then he would have got the Nobel Prize, which maybe he would have. But the thing is, I was always doubtful that little tiny black holes would be there, because I thought the Big Bang had to be very smooth, and I didn't see how they could have come about. That's not really the point here. I didn't see that. I mean, as you say, you need to get it for something which is observed, and that seems to be one of the rules. And since those black hole, what does he call them? The black hole explosions have been seen, but you see, maybe they are seen. This is a sort of irony, because this is getting back to CCC. Well, it's not that yet. Yeah. The Hawking evaporation, yes, that is what you might call it, the Hawking.
We'll have to wait 10 to the 165th years, though, to observe it.
That's the whole point. That's the whole point. We're seeing them already, I claim.
Oh, yes. Okay, so let's turn there. Eric, you're welcome to stay on this. I want to talk about conformal cyclic cosmology and Hawking points.
Can I ask one more?
Of course, yeah. Go ahead,
question?
Eric. Absolutely.
I had the bizarre fortune to have Jim Watson in my office years ago.
Oh gosh, yes.
And he was talking about his relationship with Francis Crick, who had passed. And I happened to be able to bring up on my screen a clip of Sir Francis talking from beyond the grave, as it were, about their collaboration. And I watched Jim just get misty, that there was the sense of something wondrous had half passed, and that he was still in the world to tell the tale, but Francis had gone on.
Yeah.
And then I accused him. I said, I read your book very carefully, and it really felt to me like you worked out the hydrogen bonds as soon as you found out that the hydrogen atoms on the nucleotides were in the wrong place in the textbooks.
Oh, I see.
And from Jerry Donahue, can you admit that you really did the double helix? And he said something that I'll never forget, and shocked me to my core. He said, oh no. He said, I did the inside. I did the hydrogen bonds. Francis did the sugar phosphate backbone on the outside. And then it was suddenly clear to me that the greatest collaboration in the history of science, potentially, was a pure collaboration in that you could see the work of both individuals in the structure. My question to you is there any echo of that in your work with Stephen Hawking? And I would say that since we're talking about the Nobel Prize, it's interesting that neither of you needed the Nobel Prize to win universal respect among your peers, and that is itself a signature of how profound this work is. In your collaboration with Stephen Hawking, is there a parallel to saying that you can see the intertwining of the two sets of ideas coming together as one?
That's a difficult one. I mean, it's certainly he carried the arguments that I had originally a good deal further, and you could say get rid of the Cauchy surface assumption I had in my theorem and so on. And then we wrote a paper together on this. So certainly there was a big influence in what he was doing. Some of the techniques developed, the idea of a Cauchy horizon, which he introduced, and things he did afterwards to do with the black holes, well, these were more or less done with other people, like the work on the, well, it was Brandon Carter, I guess, who, well, you have to go back to Israel, Werner Israel, who showed that the stationary solutions with horizons had to be spherically symmetrical. It was quite curious. Abe Ashtekar reminded me of this, that there was a lot of, many people held the view that black holes couldn't exist at that stage because there would be so many which weren't spherically symmetrical. So why could they exist? But it seemed to me that they could simply radiate away the multipoles and they would end up spherically symmetrical. But then the work started by Brandon Carter, and then Robinson, not Livor, the other one, David Robinson, that's right. Was there another one? I keep forgetting the names here. But they basically showed that the Kerr solution was but there was a contribution from Stephen Hawking which showed that if they weren't axisymmetric, you see, the work they did was assuming axisymmetry, and then Stephen showed more or less that they had to be axisymmetric if they were going to be stationary, which is a reasonable, good argument. So he did some. At that time, I thought that he was doing the best work of anybody in general relativity. But that we kind of diverged in our views later on, and he went off and started getting too influenced, in my view, by string theory and things like that. And also thinking that black holes, and that was, I won't go into the story there, but he tended to argue that black holes and white holes were the same in some sense, which seemed to me to be absurd if you had a classical object. Somehow he thought that the space-time was somehow observer-dependent concept, which was not the view I had. And so we did diverge.
Well, I will say that when you have people like, let's say in mathematics, Jean-Pierre Serre and Alexander Grothendieck, who came together and diverged, one of the things that I value the most is the letters that they would write back and forth arguing their points. Not only is the collaboration valuable, but the fact that you have people up at that level who find things on which they can disagree and do so productively. I have to say that it's both the confluence and the conflict that animate these partnerships. And we've seen this from Gilbert and Sullivan to Lennon-McCartney, wherever it is. There is an aspect of tension that actually seems to be very generative.
Well, certainly our disagreements were valuable to me in a sense. It did drive me in certain directions. So I had to think more deeply about things I was thinking about, but we didn't bring us together in any way because I don't know. But I haven't really talked about CCC properly.
Yes, we'll get to that. Yeah, I want to know, what did he think about? We'll get into the details of it in a minute. But what did Stephen think about CCC?
Well, I'll come to that. You see, because the answer is going to be I don't know, but I can guess what he said. You see, the story I've more or less explained about bar curvature hypothesis and all that, and then I sort of thought, well, it can't be that. It's got to be that you continue the conformal infinity to the stretching out the Big Bang. And Paul Todd, my graduate student, I think he was still a graduate student of mine at that time, and he more or less formulated the condition on the Big Bang that it should be continuable as a conformal manifold. So it's the boundary of a smooth boundary. That doesn't quite give you the bar curvature hypothesis. It gives you it's finite but not zero. He didn't want it zero because it led into trouble with the equations. And so when I said I wanted zero, because I knew from theorems, particularly I'm forgetting people's names now, Helmut Friedrich, who had shown that with the positive cosmological constant, I said, was a big factor there. And this came from a conversation, my own view of it came from a conversation I had with Jerry Ostreicher. And I remember I had a wrong reason for thinking it had to be zero, which had to do with twistor theory. And I had a way of, I thought, solving the googly problem, let's not go into all that, which required the cosmological constant to be zero. And so then when all this noise about the redshifts and the supernovae and seeing, well, it looked as though there's a exponential expansion or something going on. And I think we were going into dinner at some college, probably Wadham or something, and Jerry Oestreicher was there. And I said to him, surely all this stuff about the exponential expansion, that could be just dust, couldn't it? And he looked at me and he said, look, that's not the point. The point is that you put in a cosmological constant and it makes so many things fit so much better in cosmology. It's not just the exponential expansion observations from the reddening of the redshift of the supernovas and all that. So I thought, okay, you win, basically. And so I got converted to the cosmological constant. And this, you see, made scry, the null infinity, not null anymore, but space-like. And this is absolutely crucial, because you need something to fit onto the Big Bang, which is automatically space-like. So the fact that the remote future had you have a conformal future boundary, which was space-like, and therefore could be joined onto a Big Bang in a plausible way, was a consequence of this realization. But you see, Paul had the view that you could describe the Weyl-Curvature hypothesis in this way, but if you actually join it onto a remote future, the Weyl-Curvature has to be zero. As I said, Helmut Friedrich had a theorem more or less showing you this, which is an expectation anyway, for other reasons. And if this causes some problems in what you do after the Big Bang, and it leads you to actually creation of a very. It really makes dark matter come into the picture. So you have to have dark matter. So I think it was a good thing. Mm-hmm. But anyway, let's get back to the story.
Yeah.
I think I'd half described this before in some in this discussion, but I thought there was no. I had this idea of joining the Big Bang into formally, which seemed to be a plausible thing to do. Maybe just a guess, speculation, and nobody would ever prove me wrong. And then I had this idea that maybe collisions between supermassive black holes would produce signals which are strong enough that you might see the Weyl-Curvature would influence it. It would be in a derivative. I forget how many derivatives you need. It's maybe four derivatives, I think, before to Weyl-Curvature showing up in the next eon. But you do get an effect which would affect the matter, and you would see these rings in the sky. And David Spergel, the first person to try to analyze this, and he got interested in, I think he was trying to disprove it.
Yes.
And he got Amir Hajian to look at it, and they did various things. And the way they were looking at it was a way that, as I learned later, they would never see anything, and they didn't see anything. But Vahe Gerzajan later on came to me and said he'd been looking at this, and he'd been looking at it a different way. The difference between the two was, do you look at the sky fixing a radius and seeing whether the distribution of temperatures is Gaussian over the whole sky? And that was what David Spergel was suggesting. And I could see that wasn't going to be any use to me for the effect that I was going to come to. Mm-hmm. The way Vahe was looking at it was fixing the points and then looking at the different radii for each point. And you see that, the way he was doing it originally wasn't going to convince anybody, and didn't. And so we got into trouble with that, because analysis was not up to scratch in various ways. I didn't know anything about this at the time. But he seemed to, the questions you could see with a given center, more of these low various rings. If you saw 2 or 3, that would be what I'd expect. Because if you have a cluster of galaxies, then there have been several collisions within that same cluster, and they would look like one point in the celestial, in the cosmic microwave background sky. And so you'd see rings which are concentric. And so that's what Vahe looked for. And then after a lot of fuss and everything, we seemed to see a signal, although nobody seemed to believe us. And then simultaneous with us, doing it a completely different way, the Polish group, Christoph Meissner, Paweł Nierowski, and another Pole who was doing the numerical analysis, and they seem to see evidence for these rings too, with about 99.4%.
Yeah, I'm going to show up on the screen the analysis for this paper. So let me take a step back. I'm going to show on the screen for listeners and viewers what Sir Roger is talking about. Let's see, that did not work here. Let me undo that. So first of all, I want to go back to what this is not. So there's a famous picture of the cosmic microwave background with Stephen Hawking's initials in it, SH, and these are cold spots of significance. It's Stephen used to say. Although Eric and my mutual friend Sabine Hassenfelder thinks it also stands for her initials. But yeah, I know you've had your encounters with her too, and she can be quite delightfully persnickety. But this is not looking for Stephen Hawking's initials at all. We're talking about what you call Hawking points, which arise as a natural consequence of the persistence of memory of black holes surviving in successive eons. And so,
I thought about these things before, but I didn't face up to them because they're the one place in the crossover from one eon to the next where you don't get a smooth transition. Everywhere else, you can write down differential equations and see how would this transition be described. But the supermassive black holes, all the radiation, although you think of it as spread out, because it takes so long to be spread out, it's all completely squashed into a little point. So every supermassive black hole, all the radiation that comes out of that will be squashed into one point in the crossover surface, probably on our side smaller than the Planck length. I'd have to look at that. So.
Yeah, it doesn't appear. The Hawking points don't appear in this book in Cycles of Time. You were not mentioning that in this book. They don't appear in there. So how did it come about after the publication?
Discussions with Christoph Meissner. You see, we were talking about the rings first, and then we're talking more generally about what other things might. I can't remember all the conversations because I don't completely remember talking about the Hawking points then, but he says we did. Later on, he then looked for little rings and noticed this very strong signal. That is, you compare with 1,000 simulations, and out of for a particular size, and this is basically 4 degrees across in the sky. And this is significant because, here's the crossover surface. I have to hold it right. Here's the crossover surface. So, Hawking point, you have a black hole evaporating away, and all the radiation is concentrated in that point. All that energy comes through, and it has to come through because you can do integrals to show that it can't disappear. The mass of that object has to come through at this point.
But Roger, is that true even if it's not a singularity? Again, we have no evidence for singularity. What if there are no singularities? Someone tells you, Stephen comes down from Shemayim, from heaven above, and he asks you, Roger, my buddy, my friend, there are no such things as singularities. Does that hold true? Would you abandon the model?
It doesn't matter who. You do integrals around it. You see, it's like saying, is a charge an infinite density of charge at that point? We don't care. You do an integral, Gauss integral, and you say you've got the value of the charge from that integral around the surface. So when you've got this point, its effect, whether it's a singularity or just a huge concentration of mass or what have you, or radiation or something, makes very little difference. I mean, maybe it does at some point, and that would be very interesting. But for the moment, all you know is this energy bursts out, and it bursts out. You don't see it because you don't see anything until 380,000 years after the Big Bang. Okay, now we come back to Jim Peebles and all that sort of work, and last year's Nobel Prize. And now there are very good calculations to tell you the physics of what goes on from Big Bang to last scattering, or decoupling, or whatever you want to call it, and slightly different places, but more or less the same. Between that is a lot of physics which they calculate. This point was spread out, a little bit concentration of matter, but it will spread out to this region, which is about 4 degrees across in the sky, 8 times the full moon's diameter. And so what you would get is something like an input of enormous input of energy into that little point. It jiggles around, it has some kind of a Gaussian behavior. It ends up with a kind of Gaussian distribution of temperature. And the claim we're making is that you're seeing that Gaussian distribution. What they do is they look at a temperature drop. You take rings, the ring and of a certain diameter, and see how the temperature drops from outside the ring to inside the ring. And then you make a comparison with of the real sky with 1,000 simulations. And this particular, just 2 little slightly different diameters you take, you see amongst those 1,000 simulations, you don't see any of them which have the strength that you see in the real sky. So the real sky stands out above all of those.
And is that true? And oh, sorry, go ahead. I have a follow-up about polarization, but I'll get to that.
When you did 10,000 simulations, another 9,000. And then what used to be a 0 became a 1 in one spot, and the other one it became a 2. That tells you, you just do a little bit of statistics, it tells you that the confidence level that this is a real effect in the real sky is 99.98%. So this is a much stronger signal than we saw with the vision.
Eric, I don't know how much you've looked at this cosmological model, but what are your impressions about it from an educated layperson?
He's shaking his head.
I can't hear you. You're muted still, I think.
No, but he's shaking his head.
Oh, okay. All right. So
I'm using the international symbol for "Don't drag me into this." I don't want to say anything.
Let's see, Roger. Could you move a little closer to the camera, or tilt it down a little bit? So I have a paper that I'm showing on the screen from friends of mine on the Planck team, and they show the plots that you're talking about with significant Hawking points plotted, and they make a couple of cases. They talk about how these Hawking points would evolve or behave depending on whether or not you looked at them both statistically through all the Planck data that's available now in 2018, which includes multi-frequency and polarization. So the first obvious thing that I would do is look at these in polarization, because that is more than just doubling the information. In some sense, it's sort of squaring the amount of information or more. So have you looked at it, and does the significance hold up? Because according to them, it goes down. But what have you learned?
They looked at it with different things, and they also looked at the Planck data, the WMAP data. What I found not most convincing, but very convincing, is that if you look at, you see, there's a different analysis that Dan Hahn did to look for where these points are. You see, the analysis that was done in the paper doesn't locate the points at all. It's just an overall analysis for the entire sky. And this is where these confidence levels come from. It doesn't tell you where they are. But Dan Hahn looked specifically for points where the intensity increased at this sort of level. And he found quite a few points. Now, I'm not sure I believe all of them. What I do tend to believe is that the 5 strongest points in the Planck data, if you look in the WMAP data, they're all there in exactly the same spots. There's a 6th one in the WMAP, which is pretty strong. And you go back and look at the Planck, and you see it's there too. It's not one of the 5 strongest or the 6 strongest, but it's there. So those 6 points, which you see in both maps, I think the case is very strong that they are what we would call Hawking points.
Now, ab initio, if you took a cosmological model, a black hole density, these come from supermassive black holes, not unlike the ones at the center of the Milky Way, M87, and elsewhere. Knowing that there are many, many of such supermassive black holes, perhaps one at the center of every supermassive or massive cluster of galaxies, why wouldn't you see more than literally we could count on one hand?
2 reasons. One is you see a very small proportion of them. You see only the ones which are just at our particle horizon. You see where our past light cone goes, it hits the surface. There all lots of them in the middle. You don't see any of them. You see, with the colliding ones with the rings, you do see ones in the middle. But here, you only see the ones just on the edge. So it's a very small proportion of all the black holes. And these are only the very big ones. I think you would see a lot more than the ones we've seen. These are only the big ones. I would think a dedicated analysis of some sort, you might have to have another satellite, I don't know. You ought to be able to see a lot more. I think we're only seeing the strongest ones, which we happen to catch, which are just on that little tiny rim, little tiny surface, which is where our particle horizon happens to be. So that's the reason you don't see lots more. I wouldn't expect. I think we're lucky probably to see those ones as strong as we do. In fact, it needs working out exactly how big they are. I have a way of doing it, which we haven't actually worked out. I tried to get Christoph to look at it. He tries to get me to be more specific about how to do it.
Well, that brings up another question from one of my listeners in India who asks, for a young student such as himself or herself, what kind of directions in cosmology, if you were starting off again as a young graduate student with a bright mind and eager disposition, what would you recommend that somebody pursue?
I think there are a lot of problems, a lot of questions to answer here. There are questions of particle physics to answer. What are the error bonds? Now, when I say error bond, that is a dark matter particle. Now, dark matter, according to the scheme, dark matter should be created at the Big Bang and then gradually decay away. It's created through the equations. You see, the equations only work at the crossover from eon to eon if you introduce a dark matter, the dominant material in the universe then. Now, it has to have a half-life of something like 10 to the 11 years. So we're just about seeing the ones decaying now. But since the majority of the matter in the universe is dark matter, you probably should see quite a lot of these decays. Do you actually see them? What do they decay into? Now, I consider they decay into gravitational signals. So probably these are signals you might pick up in gravitational wave detectors. It needs a lot more work to work out what on earth these signals are like. I don't know what they're like. I just think they should be gravitational signals.
But another thing that persists, the persistence of memory, as Carl Sagan used to say, my friend in miniature here, here's Carl Sagan right there. He used to call it really related to things that survive time, especially things like your wonderful books. And I'm trying to work with our friend, let's see, I had a little glitch right here, but in the Matrix didn't like when I said Lord Eric Weinstein, or that he is going to write a book, but you are going to write a book, Eric. But Carl Sagan said a book is proof that human beings can work magic. I think black holes are kind of magical. I also think that magnetic fields are kind of magical. And is it not possible for magnetic fields to make it through the simulation?
Absolutely.
Yeah. So can you talk about that?
Absolutely. No, this is, in fact, I was going to ask you that question. That very question. No, you see a magnetic field. I mean, this is really Paul Todd, again, he was sitting next to somebody, I can't remember. It was the question that came up about primordial magnetic fields and things like that, which seem to be, you get these things in voids and where do they come from and so on.
Yes, it's fascinating.
So Paul asked me, he said, well, what about magnetic fields and galactic clusters? Should they come through? And I said, yeah, sure. Just electromagnetism. They come through like a beam of light, definitely. So you should see them. Where should you see them? You should see them where you used to have a cluster of galaxies, presumably. That's where they would be strongest. Where are they? They're where the Hawking points are. So I would guess, you ought to see primordial magnetic fields around Hawking points.
And that's something we can test, and you and I have talked about collaborating as well on this phenomenon. And one of my colleagues is a postdoctoral scholar here, Dr. Grant Tepley, formerly of Caltech and currently of UC San Diego, works in the Simons Observatory. He wants to know if you've looked at the cold spot. There's this anomalous cold spot, not a hot spot like a Hawking point would be, but a cold spot. And that's a subject of great interest because it's anomalous at the many sigma level of significance. What do you think about cold spots in the theory of conformal cyclic cosmology?
this is only a guess, so I'm not. I think people have told me where it is, but I think it is fairly close to. You see, one of the most striking pictures you get, and I don't know if you've got that one up, it's a picture that Vahe made of the Planck data. It's the paper that we wrote together on the Fermi paradox. Can you find that paper?
Yes, I'm gonna. I'll look that up. But keep describing it. It'll take me a second to.
No, what he plotted was in the Planck data, centers of low variance rings, and you only count them if you see at least three concentric rings. Three concentric rings. That's right. There may be more than three, but no less than three. And they are color-coded. Now, here's where I get confused. They're color-coded according to the temperature, the average temperature. Now, because of two backwardsnesses, the red ones are actually the very distant ones in the theory. The color coding is that the red ones are the hot ones, and so you might think of them as blue, but they're also, in CCC, it goes the other way around. That is to say, the distant signals are the blue shifted ones, because the signal is coming towards us, and therefore it's blue shifted. You won't see them if it's going away from us. Whereas the near ones, you see them if it's going away from us. That's the way the geometry works. So that there's a big splodge, the biggest splodge in the picture. If you see, have you got the picture up there?
I'm trying. It's a very low resolution, the picture that I have, but keep going.
There's a picture where you see color-coded
multiple significance levels for. Yes, I'll show that. Yep.
And you see on the bottom, sort of, you see there's the middle galactic plane is removed. So there's a whole region which is cut out. But then points which are not in the removed region, even if the circles intersect the removed region, they are included in the scheme. And the color coding is depending on, according to me, how distant they are. So if you see red ones, they're blue shifted and therefore distant. I always get myself confused there, but that's the right way around.
But the point is, the cold spot, it could be essentially a sign convention in the way that he's making the plots. In other words, or
cold spot. Well, there is a convention which I have to come to too, as I'll confuse people.
Yeah.
But let me get to that. There's a cold spot, I think, is close to the red splodge. Well, with a huge number of sources. Is outside our particle horizon. So we don't directly see the galaxies. However, we do see, according to this, the collisions between supermassive black holes in the galaxies. And so that galactic super duper cluster is only evidenced by the collisions between the black holes in that super duper cluster. So what I'm claiming is that there is or was is the right word, I guess, a supermassive black hole cluster, a supermassive cluster, let's say, of galaxies, presumably with very large numbers of supermassive black holes running into each other and producing this huge red conglomeration. Now, this is not off the top of my head because I thought of it before, but it was on top of my head then too. But maybe this huge density of galactic, and you see this inhomogeneity there, other people have to explain it somehow anyway. It's there in this analysis. Now, what it indicates is a question for other people, but we claim it is evidence of a supermassive, a super duper, I'll call it, cluster of galaxies where you're seeing the collisions of the galaxies, the gravitational wave signals from those collisions, and they're coming through. Now, if that was a huge density of material, then the material around it would be attracted towards it. Now, that could mean that material that we see within our is to some extent moving away from us, and therefore colder. So if the cold spot is somewhere around there, that's a possible evidence from these signals that the universe is not nearly so homogeneous and isotropic as people think. We see this not only from, I think very strikingly from that picture I'm trying to guide you to in Varia, you see the color, very brightly colored one. I think it's 1B or something. I can't remember the numbering.
Yeah, I'm showing them all. There's several of them, and they depend on which quadrant of the galaxy one is looking at. But I know you have an appointment coming up soon, Sir Roger, so I want to be respectful of your time. And thank you. You'll be soon picking up a special kind of hotspot when you journey and make the journey. Although it's going to be virtual, right? You're not going to be in person for the Nobel. The Nobel banquet is not taking place this year.
They don't even know what's going on, let alone me. No, they want me to be at the Swedish embassy, Swedish consulate. There's a building, a Swedish part of Sweden in London, where I have to go, which is, I'm not sure if it's the Swedish embassy, but it's part of the Swedish embassy complex. And I think the event will take place. They're probably everybody with masks on.
Yes.
And I think they may give me a medal of some sort then.
I knew it was. I knew they would find a way to punish you for leaving an encomium on my fair book somehow, and it looks like 2020 has conspired to make that come true. I want to thank you, Sir Roger, and my friend Eric. Eric, any final words for our beloved friend?
Just congratulations, and if you have any thoughts about where you think young people, younger than myself, should be charging off, I hope you will make them known to the field, because I think that your voice, newly empowered as it were by this shiny disc, is going to make a huge difference in renewing the field, I hope.
I want something clarified though before yes, I think I'm working on it. There are some thoughts about that, absolutely. Yes, indeed. Well, you may know about this thing called the Penrose Institute, which may have a revival.
Yes, we're hoping to establish that here, deepen our connections between the Arthur C. Clarke Center for Human Imagination and the Penrose Institute, which will be located here.
Let me ask you a question, which is very critical to this question. I understand from what you've just been saying, if I interpret this right, that the telescopes or whatever, is it Chile or?
Yes, we'll have telescopes in Chile and at the South Pole, Antarctica.
Oh, both. Oh, that's good. Now, presumably, you are able to pinpoint magnetic fields. Is that the question?
Well,
rather than just
the issue,
average.
The issue of primordial magnetic fields is a very rich one, because, as you mentioned, we have evidence for magnetic fields on all scales, from the human being scale to the planetary scale to the galaxy to the cluster scale, tens of megaparsecs across. But we have no evidence for an uncollapsed magnetic field, a magnetic field not associated with some gravitationally bound structure. One of the goals of the Simons Observatory is to do just that, to look for primordial magnetic field signatures, which will reveal themselves at high resolution with our large aperture telescope, the LAT, 6-meter diameter telescope that the Simons Observatory is building.
Where they are, it's not just an overall.
We're going to survey a very large fraction of the sky, tens and tens of %. Not as much as Planck, but with much higher resolution, much higher precision, and much higher accuracy in terms of calibration. For Planck was not designed, and neither was WMAP. It could do polarization, but in terms of doing it, you have to look for very subtle experimental effects that can systematically contaminate. But what's so cute, Roger, and you'll appreciate it, your friend Jim Simons and mine, he is convinced that there is a signature of Chern-Simons birefringence, cosmic birefringence, that we're also looking for. There was actually a claim of evidence for it that just came out, published by scientists in Japan and in Germany. But the issue is, you get it for free if you search for primordial magnetic fields, which presumably could confirm, or possibly, you know this as well as I do, refute our own favorite hypotheses. It could be true that we discover that there are no Hawking points. That's a possibility. But what's so interesting is we get for free constraints on Lorentz violation, on parity violation, and on things exotic physics, scalar fields, etc., called cosmic birefringence. And so we get it for free. We're going to learn a tremendous amount about this. We'll be able to test it. And who knows, you and Jim might get a second one. You might be the second person ever to get a non-chocolate Gelt Nobel Prize.
No, the other people have had to too.
Yes, that's true. Yes. But in physics, only one, right? Only Bardeen, right?
Oh, yes, that's Bardeen.
Yes, that's right. Yes.
for other topics.
So I want to thank you. I want to remind people in the Into the Impossible family that we're going to be doing a live stream with Adam Rees, Sir Roger's co-laureate. We're doing a live stream with Adam Rees, Jan Levin, Wendy Friedman, David Spergel, who you mentioned, and myself coming up this Tuesday night. We're doing live stargazing. It's the 30th birthday of the Hubble telescope, Sir Roger, and it's the 20th birthday of the International Space Station. So our partners and friends in Wyoming Stargazing, we're going to use huge telescopes to recreate the 1920s Curtis Shapley debate that concerned the size of the universe. So that's happening Tuesday night, this coming Tuesday, the 10th of November at 6 p.m. Eastern Time. I hope you guys will join in what continues to be a wonderful year of pandemic podcasting. Sir Roger Penrose, I want to thank you so much. I'm sorry I kept you so long. I can't resist. It's too difficult when you have good friends to chat with. I wish you all the best. Congratulations, a hearty mazel tov, as we say, and all the best, Roger. Be well, be healthy, and continue to do great work and inspire billions around the world.
Thank you so much. Yes.
Bye, gentlemen.
Goodbye.